So, all right, let's get started. So first of all, thank you so much for coming to this session, which is the last session of the day. Today's topic is the cost of learning from the best. We'll be discussing how prior knowledge weakens the security of deep neural networks. So let me take this opportunity to introduce our team a little bit. So our team is called XLab. This is the security lab within Baidu organization. It is led by our chief security scientist, Dr. Tao Wei. And one direction of the research is AI security research, which is this topic falls into. And my name is Zheng. I'm leading this AI security research efforts in the team. My research focuses on, mainly focuses on adversarial machine learning, especially deep learning. Basically, we explore the latest advanced attack mechanisms to the deep neural networks, as well as the defensive mechanisms. We also spend lots of efforts improving the robustness of deep neural networks. So if you are interested, feel free to come to me and we can discuss more detail offline. One of our key speakers, Dr. Yunhan, who cannot be here because of the visa issue, so I'm taking his position to do this presentation. We also have Yulong Zhang, who is leading the system security research. We also have lots of open source projects like MesaLock, MesaLink, MesaPi. These are all under the big umbrella like MesaT, which is memory-safe, trusted execution environment. Trusting environment, yeah. So feel free to check out these open source projects. And we also have Yantao, who is the intern with us in the past a few months, who also contributed a lot to this project. So in today's topic, we'll be mainly discussing a black box approach attack against the vision-based deep neural networks. We'll be focusing on the models deployed behind the cloud-based services. The thing we're trying to achieve is by applying perturbations to the original input images so that the cloud-based services, instead of correctly identified objects within the images, we want to achieve the attacks such that these cloud models won't be able to detect the objects within that image. For example, he cannot detect the black SUVs in this image. So talking about cloud services, this reminds us lots of big players like Amazon AWS, Google Cloud, Microsoft Azure, as well as IBM. They provide lots of machine learning capabilities like those kind of like image classification capability, object detection capability, as well as the natural language processing capability. Also, you can find some malware classification capability. However, the question we have is, are these cloud models safe against the adversaries? So the answer is no. I will just walk through a simple case study to explain that. So we pick a Safe Search API, which is the Google Safe Search API as an example. So this API, what it does is we take an input image and it returns a results like different categories for this image along with the confidence levels. The confidence levels is from 1 to 5. 1 means very unlikely, and 5 is very likely. So in this case, this point image will be considered to contain adult content as well as the racy content. So is this kind of search API can be easily deceived? This is the question we have. The answer is yes. So we actually apply several spatial transformations to the original image in this case, which is the leftmost image. When we feed this image into Safe Search API, the API returns the rankings for adult and racy at 5, which is very likely. But when we apply the several spatial transformation, for example, framing, we zoom out the image and add a frame around it. And also we do a perspective transformation. Basically, we stretch out four vertices a little bit to make it to a different shape. And also apply a affine transformation. So we basically rotate image a little bit. So for all of these transformations, we can see when we feed those images to Safe Search API, the ratings for the adult and the RACI, they can be lowered to unlikely, like 2 or 2 below. In addition to that, we actually run an evaluation against this Safe Search API, basically crawl 100 images. And for each image, we run 100 different spatial transformations so that we can have like 10,000 images as a test data sets. And we use the 10K image to run against the Safe Search API, and here is the results. So out of 10K test images, 69% of those has the rating of the adult less or equal than 2, which is unlikely. So out of 10K images, 40% of those has both adult and the RACI ratings less or equal than 2, which is also unlikely. So we actually gave a thought about that and see what caused that. So there are 2 reasons we thought. So one is during the training, probably they don't have enough spatial data augmentations included in their training data sets, so that the training models won't include the data distributions that can detect such transformed images. Secondly, those Safe Search API will assume that the input data will include the region of interest that can include those objects that they are going to classify. However, oftentimes it might not be the case. So pre-processing will be a necessary step needs to be done. So in this case, probably there's no pre-processing step using this API. So here we have another question. So is this simple spatial attack generally applicable to all the rest of the cloud-based vision models? The answer is no, because we actually run a test against the object detection API. It turns out that object detection API is really robust against such simple spatial attack. As we can see from the images down below, also the leftmost image is the original ones, and the right 3 images is the one we applied the transformations. So you can see once we feed those images into the object detection API, what they return is they can correctly draw the bounding box around the 2 vehicles. So that means no matter how we run the transformation, the object detection API is very robust against it. So the reasons we thought about that is probably for the image classification model, as we discussed previously, they only have one objective, which is to lower the confidence levels of the targeted class. But however, in the object detection API, they have multiple objectives. For example, they need to detect multiple objects in the image. They also need to derive which class or which category this object falls into, and also they need to derive or predict the size as well as the location of the bounding boxes, and also they need to predict the confidence score of the objects. So it might be easy for the attacker to achieve the successful attack against just one objective, but combine these together, but it will be harder for the attacker to achieve attacking all of these objectives. For the rest of the talk, we'll be discussing how we achieve this attack by using a method we call fingerprinting attack that can generate adversarial example very efficiently against these cloud-based vision models. So talking about adversarial example, I will just use one slide to briefly introduce that. So given this example, like two images both on the left and right, if I don't tell you the difference, probably most of the people will think these two images are identical. However, the difference is actually the middle image, which is the perturbation we apply to the original image on the left, which results into the image on the right. And once we feed those two images into the object detection APIs, what it returns is for the original image, it can correctly identify two vehicles in the image. However, for the adversarial example, he can only detect the white van in the image. He won't be able to identify the black SUV in it. And at the same time, the confidence level of the white van is lowered. So in order to generate adversarial examples, usually the attacker has to have a white box access to the model because they need to use gradient descent kind of method to calculate the direction of the changes to the original inputs. And there is different levels of the knowledge that the attacker can have. For example, they can get access to the entire training data set, or they can have the access to the model architecture, or they can have the access to the model parameters. If they can access those, it is considered to be a white box. But most of the time, the attacker might not have such privileges. What they have, they might have just the last layer logics from the model, or they can have just the prediction values from the models. So in that cases, it is considered black box. So in our talk, we consider the cloud AI models are black boxed models to the attackers. And we argue that the black box just provide a false sense of security. And in the rest of the slides, we'll be discussing how we achieve that by leveraging a vulnerability we found in the transfer learning, which is being widely used in the deep learning community to train the model. So first of all, let me just introduce transfer learning a little bit. So in this image, the top part is a ImageNet kind of architecture, deep learning neural network architecture. So basically, if you want to train a deep neural networks, what you need to have is a huge number of data sets, like millions of data images. And also, you need to have lots of GPU resources so that you can train a model within days or weeks to have a model with high accuracy. However, normal users might not have access to these kind of resources. What they have probably just a few training examples, which is just black and white X-ray scan images. And what it spits out is only like 4 categories instead of 1,000 categories like what ImageNet has. However, if we use a transfer learning, which actually you can inherit a pre-trained model from the ImageNet, by fine-tuning the model, you can train a new model which has the same high accuracy within just minutes or just hours. Let's use another example to illustrate the idea more clearly. So suppose you have a teacher model. You want to train a number of student models. And here is the architecture of the teacher model, and we use a dotted line to divide the models into 2 parts. The left part, we consider that as feature extractor layers, and the right part is considered to be a classification layers or the fine-tuning layers. So when the student trains his own models, he inherits the entire architecture from the teacher and add a few classification layers to the end, and they just fine-tuning the classification layers to achieve the new model. At the same time here, the point is the entire feature extractor layers, no matter whether this is both the architecture and also the parameter values remains the same. So this is the opportunity we have that we can run the attack against the deep neural networks. And here's how. So we use the Yulong v3 as an example, and the Yulong v3 is the state-of-the-art object detection model. So given an input image, it will learn through the feature extractor, and they will be propagated to the rest of the classification layers to detect the object within the image. So the idea is, if we can fool the layer K, which is the layers in the feature extractor part, then probably we can fool the entire model at the end. So here, for simplicity, the K we will be referring to the last layer in the feature extractor. So instead, in order to carry out a successful attack, we break it down to 3 steps. So first of all, we need to identify which feature extractor the model deployed behind the cloud services is using with just a few queries. Secondly, we will generate adversarial examples on white-boxed pre-trained models. And lastly, we'll attack the black model using the training adversarial example we obtained from the previous steps. So here, I will illustrate our approaches. In this example, again, suppose we have a benign image, which is a cat. When feeding to the deep learning models, and also the dotted line divided the model into 2 parts. The left part is the feature extractor layers, and the right part is the classification layers. So if we look at the last layers, and the largest of the neuron outputs of the last layer in the feature extractor, and we can see one property we call dispersions, which can be measured using the Zhenyu coefficient or standard deviations. So here we just use the standard deviation to illustrate the dispersion values. So basically, the last layer of the feature extractor has a dispersion value at 0.39, which is considered to be relatively high. So when this value is propagated to the end, the final layer will have a very high confidence that the input image is classified as the cat. So what the attacker can do is he can intentionally craft an example such that he can lower the dispersion values in the last layer of the feature extractor. In this case, we can target to lower the standard deviation for the last layer to close to 0. In that case, when this value is propagated to the end, then we hope that the confidence score of that category cat will be also very low. Thus, we can achieve our successful attack. Again, since we are trying to figure out which feature extractor is using by the cloud models, so what we do is we collect a number of publicly available feature extractor, as well, in other words, like deep neural network architectures that is open sourced. For example, the VGG16, VGG19, Inception, ResNet, MobileNet. So these are publicly available. So for each of these architecture, we were trying to create an input example that minimize the last layer, the dispersion values of the last layer of the feature extractor. Once we have that, we will monitor the output of the last layer, right? Then we do the comparisons. And here is the results. So basically, we collect like 14 different kinds of feature extractor. And among these 14 different feature extractor, and the y-axis is the confidence score of the cat. And here we see the F6 and F13 has the lowest confidence scores, which means these architecture might be the ones are used by the models deployed behind the cloud services. And for each of these candidate architecture, we'll run an iterative gradient sign method to create different adversary examples. So when we're creating such adversary examples, actually there are different strategies. First, we can run a untargeted attack by just minimizing the last layer largest, the last layer's dispersion values in the feature extractor, such that once that is lower, then the last layers, the final score will be lower as well. Secondly, which we can do is to target the last layer, which we can do a targeted attack. Basically, we want to maximize the distance between the original class and the targeted class that the attack wanted to be. So once we maximize the distance, then we can achieve such a targeted attack. And now, here is the evaluation part. As usual, we'll show the evasion rate. At the same time, I want to bring up another idea is the efficiency, which is the number of queries that the attacker will use to achieve this successful attack. This is very important because as a black box attack, especially in cloud-based kind of models, the attacker only has the access to make a query against this API to get some information from the model. So the more queries they query, so probably they will be charged a lot for those kind of attempts. So this is very bad for the attackers, right? So that's why the efficiency is very important. So here we compare two attack methods here, along with two how many budgets do you have on the attacks. So suppose for the dispersion kind of attack, if you have just two queries for each input test image, so the evasion rate you can have is like 33%. So if you have like more budget, like 100 queries for each image, then the evasion rate will be increased to 86%. For the target score attack, suppose you have two queries for each input image, you can achieve like 16% evasion rate. If you have more budget, like 100 queries per image, then you can have a higher successful rate, like 65%. Also, the image down below shows the effectiveness of this attack. By using the target score attack as well and the dispersion attack, the object detection API won't be able to tell the black SUV in the image. And even though they can detect the white van in the image, however, the confidence score is significantly lowered. Now, let's come to the conclusion and the takeaways of this talk. So we argue that black box only provides a false sense of security, and fooling the prediction result by targeting the internal layers is generally applicable to the deep neural networks. And we call for efforts to harden the models with adversary trainings. So that's pretty much of the talk. So I'm open to questions. Yes?
Could you show a pair of images and do you have visible differences between them? I'm curious whether it's only the color difference or how are they different?
Difference between original image and adversary example?
Exactly.
Okay, here is the, hold on, where is it? Okay, the difference is in the middle, as you can tell. Can you tell the middle image? So these are just pixel-wise perturbations. So basically, you make changes to each pixel a little bit based on like very popular methods based on the LP norm kind of methods. I can do like L1, L infinity, L like L2, those kind of things, L0. Yes.
Could you please explain more details the fingerprinting?
Oh, the fingerprinting? Okay, sure. Let me see. Here is the fingerprinting. Okay, right here. Yeah. So the fingerprinting basically is that you need to identify which feature extractor is being used, right? So the thing is, so the property we can observe here is the last layer of the feature extractor. The property we call is dispersion value. In here, we use standard deviation to calculate this dispersion value, right? So for the benign image here, the top one, so it has a standard deviation for the last layer of the feature extractor is like 0.09. These are calculated based on the largest of the neuron outputs from the last layer of the feature extractor. Okay, so the thing we are trying to do is we can just minimize this dispersion value such that the standard deviation of the last layers based across all the largest, we can make it close to zero. We can intentionally create such input to achieve that, right? So our optimization goal is to achieve that. So we hope when the output of this last layer of the feature extractor being propagated to the final layer, then the confidence level of the target class cat will be lower. Hopefully it's below the threshold. So in that case, the image classifier won't be able to detect this input is a cat. Does that make sense?
Maybe I misunderstood.
Uh-huh.
Because there's a goal of fingerprinting, find out what original network
Okay.
used
Yeah.
to create these features.
Right.
Because you don't see these logics.
Okay.
You see the output produced by the
Okay. Yeah, I missed something right here. So basically, you have this, right? So here we explain the idea how we can create such image. Now we want to find which architecture being used by the cloud models. So the thing is, you have a number of architecture out there that's publicly available, right? So for each of those, we can use the same method we introduced here to create an input, right? So suppose there are 14 different feature extractors here, then we can have 14 different inputs. Are you with me here?
You need to know which one was used for this specific.
Right. Right now, I don't have to. I just have I just collect 14 like publicly available architecture. I don't know which one it is used by the cloud models. Right. Okay, great. Answer your question. Nice. Yes. Oh, defensive mechanism, that's a great question. So there are a number of ways have been proposed. So one thing is when you do the inferencing, you probably can add randomness to the input data. For example, you can drop a few pixels to the original inputs. And also there could be other ways like you can, when you train the model, you can try to increase the distance between your student model and the teacher model. I mean, the neuron distance as a regulation kind of part. Right, so this is second one. So other things probably also you can do is to use ensemble method. So basically you can, when you deploy model, instead of deploying just one model, you can deploy a number of student models that learn from different teacher models. So you can run like a majority vote on these student models to see which one, what is the results it is, right? So the attacker has to deal with all these kind of teacher models. So it might be harder for him. Hope that answers your question. Great. I guess that's it. Thank you so much.